Welcome! Today we are exploring the fascinating world of thermal expansion and heat transfer. Have you ever wondered how a classic glass thermometer works? The fluid inside expands as it gets warmer and contracts as it cools.
When we talk about linear expansion, we mean a change in a material's length due to heat. Different materials expand at completely different rates. We calculate this change using a specific multiplier called the coefficient of linear expansion. This coefficient is crucial. For example, steel and copper have very different coefficients. If you take identical rods of both materials and heat them by the exact same amount, they will expand to different lengths. It is not just length that changes, volume expands too. The formula is very similar to linear expansion, but here we use a volume expansion coefficient, which is actually 3 times larger than the linear coefficient for that material. This is a massive safety factor in the trades. If you store a tightly sealed, full container of liquid near a heat source, the expanding liquid has nowhere to go and can actually cause the container to violently burst.
Because the pressures created by thermal expansion are absolutely astounding, large structures like bridges, roadways, and commercial buildings must have expansion joints built directly into their design.
Without these carefully designed gaps, the massive force of expanding steel and concrete during hot summer months would cause severe structural damage, including cracks, squeaks, and dangerous distortions. Now let's shift to how heat actually moves from one place to another. Heat always flows in one of 3 distinct ways: conduction through direct contact, convection through fluids, and radiation through electromagnetic waves. Conduction happens when heat travels directly through a solid object, but not all materials are good conductors. Materials that strongly resist heat flow, like fiberglass or cork, are used as thermal insulators in construction. We measure this insulating ability using an R value. The thicker the material and the lower its thermal conductivity, the higher the R value. A high R value means the material is excellent at keeping heat exactly where you want it. Convection is the transfer of heat by the movement of fluids, which includes liquids and gases. When a fluid heats up, it expands, becomes less dense, and naturally rises, while the cooler, denser fluid sinks to take its place. That continuous loop is natural convection. We also use forced convection in the trades. For example, a car's cooling system uses a mechanical pump to actively force water through the engine block to pull heat away. Finally, we have radiation. Radiated heat travels just like light through empty space. How well an object absorbs or emits this radiant heat depends heavily on the color and texture of its surface. We measure this using an emissivity value, or E value. A dark matte surface has a high value and absorbs heat extremely well, while a highly polished, light-colored surface reflects the heat away. To wrap up our session, remember that heat causes materials to expand in both length and volume, creating immense physical forces. Furthermore, heat always transfers from warmer to cooler areas via conduction, convection, or radiation. Great job today.